So it's a pleasure to introduce our next speaker, Professor Danny Halperin from Tel Aviv University. Danny, take it away.
Thank you very much. Hello, everybody. I'm very glad to be here and have the opportunity to speak to you. The more precise title of my talk is, do we still need classical robot algorithms? It's a question that I'm asked on a daily basis. Let me start with a riddle. I use the term riddle for a question to which I know the answer. Later on, I'll use open problem for questions that I don't know the answer. So here's the question. I give you two Roombas, a red one and a blue one. These are the full-colored disks. And then I ask you to move them into the corresponding circle. They need to avoid each other, and I ask you to do it in the shortest possible way, such that the sum of the lengths is minimized of all possible tracks. So I guess you see the solution of this question, but I want you to be ready for every situation and think, for example, about this situation. And think about it where I quickly tell you about my path in robotics. I started by working out of undergrad studies. I went to work for a robotics CAD company. I worked there for over 4 years. I did robot kinematics and trajectory planning. It got me excited on robotics. I went to study the theory of motion planning through computational geometry and arrangements of curves and surfaces. Then I did my postdoc at Stanford, where I worked on more applied aspects of robot motion, and I was introduced to assembly planning. Then as a professor, I worked for a long time, again, on a problem inspired during my work in the company where robots would disintegrate on the screen on how to implement algorithms robustly. And now I'm back to robot motion and assembly planning, doing robot kinematics and trajectory planning, and I'll tell you about it more soon. So the reason people ask me this question all the time about robot algorithms, because there is a perception that everything is solved or soon will be by AI. I will take two examples, optimization of the motion of a fleet of robots and what I call holistic automation of assembly planning, where I don't see that this is currently the situation, that data-driven approaches will solve everything, at least for now. So let me start with optimizing the motion of fleets of robots. I'm showing you examples for two robots to start with. It's not because I'm not interested in more, I'm interested in many more, but even for two robots, there are many things that we do not know. So this question, which was open for a long time, was solved very nicely by Kirkpatrick and Liu. They characterized how the optimal paths look. It took us several years to adapt their solution to the case of two squares, but this is now known. But the following problem, the solution to it is not known. Instead of minimizing the length of the path, I ask you to minimize the time to execute the solution. And we do not know the answer to this question. So let's get back to the shortest path where we know the answer and add obstacles. Once we add obstacles, not only don't we know to solve this question, we do not even know if it's NP-hard or it has a polynomial time solution. So I guess some of you say that this is all theoretical rubbish and that you probably can solve these questions one way or another. And I want to warn against this line of thought and give an example from the history of sampling-based planning. I'm not going to explain what it is if you don't know what it is, but it started with PRM. Suddenly, many questions that were not solvable earlier became solvable with very easy programming, sometimes slow, and then RT was presented, and not only everything was solvable, it was solvable pretty fast. You could notice that the quality of the past is bad. And when you talk to people about it, they say, don't worry, just sample more. Or I have my own tweaks to handle this. In fact, we proved formally that RRT produces horrible results with high probability, sometimes 100 times longer than the shortest path, until we fortunately had Karaman and Fazoli, who told us what we need to do in order to converge to optimality. They gave us the theory, and it worked in practice. So it seems like optimization of motion for fleets of robots is now solved, and I want to tell you that it is very far from being solved. We are making those pictures are from our papers, sometimes for a few complex robots, 10 robot arm manipulators, sometimes for hundreds of robots. But state-of-the-art sampling-based planner, specially tailored to multi-robot, can only cope with very small number of robots. People don't realize it. Say, I'll just take all my robots, I think of them as one big composite robot. It works for a very small number of robots. We know, we experiment intensively with this. We have a system, it's called Disco PyGal. Disco because of the disks of the Roomba, Py for Python, and Gal for the SIGA library underneath it. If you ask about time optimality, then the situation is really bad because we know almost nothing. The papers allude to the fact that probably it's not hard to generalize. Nothing is proven yet. So again, I think these are very crucial questions. If you believe in robotics, I believe many of you do, then eventually in various situations like firefighting or disaster zones, being optimal in time could be a matter of life or death. Now, let me be slightly less dramatic with my next example, which I call holistic automation of assembly planning. This is structured environment. Everything is almost under our control. And here is what I'd like to happen. This is the aspiration. I give you a design of the product. This is how it looks assembled. And I want you to give me a full operative robotic assembly plan. Namely, give me the digital model of your product. Tell me what are your robots. You'll put it in my system. I'll press a button. And then I'll download my programs into the robots, and the robotic cell will start to play. Reality is different. First of all, almost every question in assembly planning is a very difficult form of motion planning. You have to make choices between sets of parts, and you have to move in very tight quarters. The number of hands, it's a very interesting topic in assembly planning. How many different sub-assemblies you need to move together. Sequencing, accommodating physical constraints. You typically, when you move a sub-assembly, you want the parts to be connected. Robot placement, there are many interesting and hard questions here. The surprising fact is that even the most advanced manufacturers, you teach the robots assembly tasks by hand. Search Google for assembly in Tesla. They talk about months and months of work of engineers to teach the robots what to do. Now, the big manufacturers can afford it, but small, medium businesses cannot afford it. So I think I was glad to see that Alison Okamura in her talk yesterday listed manufacturing and assembly at the top of the needs from society, from robotics. So making a progress here can have societal impact. The sim to wheel here is particularly difficult. I showed this to a robotics reinforcement learning expert and said, oh, these are too many peg in a hole concatenated. I cannot do it with reinforcement learning. I don't know, perhaps someone else can do. I want to tell you about recent work that my students presented earlier today, where we take one step in assembly and we fully automate it. We take the digital models of the parts and the model of the robot, and we give a complete motion plan. On the right-hand side, you will see the alpha puzzle introduced by Nancy Amato to motion planning 30 years ago. For 30 years, it has only been solved in simulation. And here, it's the first time that a robot carries out the solution. On the left-hand side, you see a more complex version of it. It's the Z alpha puzzle. And in the middle, it's a feature from a data set of hard assembly tasks. Now, I mentioned that number of hands is a critical parameter. When you have only two parts, there's nothing too much to talk about. You need two hands, and you don't need two robots. Two hands, it can be a fixture in a robot. But we use two robots for two-handed assembly because it gives you various advantages, in particular faster time, more flexibility in robot placement, some control about the relation between the robots and the environment. Okay, let me make a few final notes. I'm not the only person in this conference talking about what others refer to as the elephant in the room. Many people ask this question. Tomorrow there is a debate whether data will solve all the problems in robotics. I chose a few citations. There is a very nice survey in IEEE Spectrum covering many opinions about this question of data-driven versus model-driven solutions. Don't worry, people think these are theorems. No, these are take-home messages. Let me start with a very naive one. Robotics is important. It's trivial. I guess that's why you are here. Some of you may not know, but robotics is difficult. It's very difficult to make a meaningful research contribution. It's extremely difficult to start and sustain a robot company. But this combination of the two make the algorithmic challenges fascinating. These are deep questions, and at the same time, they are relevant. Don't neglect robot algorithm research. It should not interfere with your machine learning aspiration. You can always combine them. But perhaps the most important take-home message that I didn't manage to get myself to write it down is be accurate and responsible in stating what current robot technology can do. I chose 2 out of 10 problems on which I wrote a survey. We call them geobotics because they are geometry intensive, written with my colleague Mikkel Abramsen, who is Danish. That's how we got to the UR factory. But I chose 2 that really have meaning, and they are not just intellectual games. They can have some impact. I want to thank my students, some of my former students, my collaborators, and the funding agencies, and you for listening.
Thanks very much. Time for a question? Okay, so always take the opportunity to ask my questions if I can. At the very end, you make this fascinating recommendation that we should be combining algorithmic approaches with data-driven approaches. And I wonder if you can speculate a little bit on the ways you think that can work the best together, right? So,
I see it all the time. I mean, there are some small or local problems that we don't know how to model, and it's good. Sometimes some type of collision detection you can do better nowadays with machine learning approaches. Learning some kind of dynamic behavior. There are good reasons to use it. I don't see it solving for the two problems that I mentioned the full problem.
Okay. All right. One final question.
So we have search, we have continuous optimization, we have data-driven methods. Are those enough, or are we still missing a fourth tool that is the thing that will let us solve these open problems?
It's a wonderful question. I wish I knew. I think this is the best thing to look for, something new. But I'm too old for that.
All right, well, let's thank Danny one last time.